Hello, this is my presentation of my gas law phenomenon, can collapsing.
Would you ever have it on your arm? I need a little
water.
In this,
That was a good one.
Shut in there, pulse a bit low.
Quick, it upside down.
Hey. Quick.
in this demonstration, as you can see in the beginning, they are heating
Would you ever have it on your arm?
the can and it's steaming, so water is coming out of the can. There's only a small amount of water and it's being heated into steam. And then it is being submerged quickly in water, which closes off essentially the opening of the can. This is my model of this collapsing can phenomenon. So my drawing over here is kind of showing you that before heating, if you were to just have that can sitting out, the number of gas particles kind of per unit of volume outside of the can is going to be equal to the number of particles, the spacing of the particles in the inside of the can. And because of that, the pressure of the gas inside of the can is equal to the pressure of the gas of the atmosphere pushing on the outside of the can. After heating, the steam that came out of the mouth of the can caused there to be less gas particles inside of the can than outside of the can. The number of particles stayed the same. So the atmospheric pressure on the outside of the can stayed the same, but now there was a partial vacuum created and the pressure inside of the can was much less, which is what causes the implosion. So this is my explanation and my gas law. Before heating, the pressure inside of the can, the ratio of the pressure to the number of moles in the can inside of the can is equal to the pressure, atmospheric pressure, and the number of moles in the atmosphere. This is not officially a gas law. It's not Charles Boyle's or Gay-Lussac, so I left this blank. But a lot of your phenomenon that you pick will be one of those gas laws. After heating, the pressure of the atmosphere is much greater than the pressure inside of the can. The number of moles in the atmosphere per unit of volume is also much greater than the number of moles inside of the can. Here is a math problem that I constructed. There are let's say there's 3.5 moles of gas around the outside of the can, and the atmospheric pressure is 1.1 atm. And then once it was heated, there were 0.5 moles of gas inside of the can. So my question is, what would be the new pressure inside of the can? This is my solution, my ratio of the atmospheric pressure and the moles in the atmosphere. And then X is my new pressure inside of the can, and the ratio compared to if I have 0.5 moles of gas inside of the can. So when I do the algebra and I solve for X, I get 0.013 atmospheres, which makes sense. It should be much less pressure in the can than out of the can with less moles of gas. Here is another gas law problem, the ideal gas law, PV equals nRT. The volume of a can is 355 milliliters, and if there are 0.0025 moles of gas inside of the can after heating to 100 degrees Celsius, what would the pressure inside of the can be? So the solution here, when we use the ideal gas law, Our volume needs to be in liters, so I converted to liters. I have moles. I also need my temperature in Kelvin, and then I'm going to use the ideal gas law constant 0.0821. Liters times atmosphere over Kelvin mole. When I substitute the pressure as my X, I can substitute everything else. And then when I do the algebra and solve for P, I end up with 0.216 atmospheres. Again, making sense that the pressure is lower in the can. That is my presentation. I hope you enjoyed it.